Hey everybody, alright, let's go through the basics of how to make a phase change diagram and also how to use that table of physical energy constants in order to finish multi-step energy problems. Alright, let's get right down to it here. Here are the things you should have out in front of you. Now from the website that you are watching this video from, you were also able to find the phase change diagram and also the table of physical energy constants. So those two are definitely something you should have in front of you. I think the phase change diagram is something good you should always look at, so you should know how to draw one, because for each of our energy problems, we do need to know how to draw the energy diagram, or the phase change diagram rather. And the table has all that information that we need for all of our problems, okay? So on we go. So this is what the phase change diagram looks like. We saw this in class. Real quick, what we are seeing here is on the X and Y axis, all right, we see two very important details. On the Y axis first, we see temperature, okay? 2 points that are always labeled on our phase change diagram. Right here is the melting point or the freezing point, and right here is the boiling point or the condensation point, all right? Now that's going to differ for every single different substance. For example, it's different for water than it is for ethanol. Okay, water freezes at 0 degrees Celsius, whereas ethanol, for example, freezes at negative 117 degrees Celsius. Very different data, but you're always going to see the melting point and the boiling point on our y-axis. Now on the x-axis, we have heat energy, okay? So as we move from left to right on the x-axis, we are adding energy, whereas if we move from right to left on the y-axis, that would be an example of the substance losing energy. All right, let's take ourselves through this phase change diagram real quick from left to right, just like we did in class. Down here on this portion of the graph, this is a solid heating up if we're moving from left to right, okay? That represents a solid heating up, and this portion right here, I will change color so it's easy for us to see. Right here, this portion horizontal, I do not see any delta T there, okay? There's no change in temperature. That is because it is a phase change. We are moving from solid to liquid, okay? That is a phase change. That is a solid melting into a liquid. The next stage here would be liquid heating up. This portion right here, I see a delta T. That is liquid heating up. After that portion, we see boiling taking place. So that is a transition from a liquid to a gas. And then finally, once we are in a gas, we can actually see that gas increasing in temperature. All right? Remember that these sections here and here do not have a delta T, so we are going to use these new equations for heat of fusion and heat of vaporization, okay? That special term, heat of fusion and heat of vaporization. Fusion is the special word that encompasses both melting and freezing, whereas vaporization is that special word that encompasses both boiling and condensation, all right? Now, just like we have the heat equation for when the change in temperature exists, we have a special equation for energy during fusion or during vaporization, okay? For fusion, that equation is Q, which is energy, equals the mass of the substance times the heat of fusion. The heat of fusion is a special given value that you will get from the physical energy constants table. For vaporization, the energy required to do this equals the mass of the substance times the heat of vaporization. All right? Remember, heat of vaporization, just like heat of fusion, is a given value on the physical energy constants data table. All right? And those two values, heat of fusion and heat of vaporization, are really similar to specific heat. Remember what specific heat means, okay? Specific heat is the amount of energy required to heat 1 gram of a substance by 1 degree Celsius. Now, that's a great value. We understand what that means. We've spent a lot of time on it. Heat of fusion and heat of vaporization is similar. However, we don't have a change of temperature that takes place during fusion. We don't have a change of temperature that takes place during vaporization. So we can't have 1 degree Celsius as part of these values like we do for specific heat. All right, specific heat is the amount of energy it takes to increase the temperature of 1 degree Celsius by blah, blah, blah. Well, we can stop right there because 1 degree Celsius is part of that little equation. That does not exist in heat of fusion or heat of vaporization. Okay, so a different value requires a different definition. So the definition of heat of fusion is the amount of energy it takes to melt or freeze, to undergo that fusion process. All right, there is no change in temperature. How much energy does it take to get us from a solid to a liquid? How much energy is released as we go from a liquid to a solid? That is heat of fusion. Whereas heat of vaporization is how much energy does it take to get us from solid to liquid? Oh, I'm sorry, from liquid to gas. How much energy is released as we go from gas to liquid? All right? And that, just like specific heat, is in terms of 1 gram of a substance, which is why that equation requires us to multiply that heat of fusion by mass, or multiply that heat of vaporization by mass. All right. Now let's take a look at what that heat of vaporization, or I'm sorry, that the physical energy constants table looks like. This is what you should be seeing. Now this looks kind of overwhelming, but it's organized very well. Okay. On the far left, we see all these different substances. Okay. We've got aluminum, we've got bromine, we've got tons of different things. For example, right down here, something we're very familiar with is water. Let's look in terms of water. Okay. This first column here, specific heat, we're familiar with that unit, joules per gram degree Celsius. Now, what we have not discussed yet is why there are 3 different specific heats for the same substance of water. Okay? Every single problem we've done so far using the heat equation, we have dealt with liquid water. Think about it. The ethanol lab, liquid water. The specific heat of a metal lab, we use liquid water. Well, not every problem requires us to use liquid water, okay? And it takes different amount of energy to increase the temperature by 1 degree Celsius of 1 gram of solid water versus liquid water versus gaseous water, all right? Ice, liquid, and gas water all have different specific heat values. And check this out. It takes 2.1 joules to increase 1 gram of ice by 1 degree Celsius. It takes 4.184 joules to increase the temperature of 1 gram of liquid water by 1 degree Celsius. It takes 1.7 joules to increase the temperature by 1 degree Celsius for 1 gram of gas, like water vapor, okay? Those need to be used, and you will have this table available to you all the time, okay? I'm not going to have you memorize this entire table. That would be kind of pretty unreasonable, all right? The heat of fusion is also provided to us. That's the amount of energy it takes to melt or freeze 1 gram of water. Heat of vaporization, the amount of energy it takes to go from a liquid to a gas, or how much energy is released as we go from a gas to a liquid. And then, very important, in order to make our phase change diagram, we see the melting point and the boiling point of this substance. For water, we know that it's 0 and 100 respectively. But for some other substances, that's something we're not familiar with. So we need to be aware of how to use this table. Okay? So if I were to say, hey, what temperature does copper boil at? I would say, all right, here's copper. I'm going to follow this right across until I get to the boiling temperature. So 2,582 degrees Celsius. If we were at that temperature, copper would actually be boiling and turning from a liquid to a gas. Okay? That's how we're using this table. Very simple, very straightforward, but we need to be familiar with how it's organized. All right. Let's put it all together. If we have a multi-step problem, okay, that means that, yeah, there's a change in temperature. We're going to be using the heat equation. But this problem takes us from not just within, we're not just changing the temperature of liquid water. We're actually going from solid to liquid, changing the temperature of that liquid, going from liquid to gas. There is a phase change involved somewhere in this problem, okay? That's why it's called multi-step. We can't just use the heat equation. So let's try one of these here. Multi-step sample problem number 1. How much energy is required to change 22 grams of ice at negative 12 degrees Celsius to liquid at 21 degrees Celsius? every single time that we do a multi-step problem, you should always, always, always start with a phase change diagram, okay? Now, we're talking about ice here, so this is water. I'm going to draw a very simple phase change diagram. I need to be familiar with this shape here, okay? I know that right there and right there are two important values. Right there is the melting point for water. That's 0 degrees Celsius. Right here is the boiling point for water. That's 100 degrees Celsius. Now, on this little graph here, I want to understand what portions I am thinking about, okay? How much energy is required to change 22 grams of ice at negative 12 degrees Celsius? I want to highlight on this graph where this occurs, okay? Where are we on the graph if we have ice at negative 12 degrees Celsius? Well, if this point right here is 0, then somewhere down there is negative 12 degrees Celsius as a solid, okay? We are going from that point all the way to where we are a liquid at 21 degrees Celsius. All right, I know that in this middle diagonal portion is liquid, so let's say right there is liquid at 21 degrees Celsius. So I see 3 parts to this problem, all right? The first part is right here. That is a solid heating up, okay? If it is a solid heating up, that means there's a delta T. So I can use the heat equation for that. That's exactly what I'll do. Q equals M times specific heat times delta T. In this case, the mass is 22 grams. The specific heat for a solid, okay, the specific heat for solid water, for ice. I'm going to look that up on my physical constants chart, and I can see that specific heat for solid water is 2.1 joules per gram degree Celsius. So I'm going to plug in 2.1 here. The change in temperature for this portion, okay, not the whole thing, for this portion right here, we are going from negative 12 degrees Celsius to 0 degrees Celsius. So we have a change in temperature of 12 degrees Celsius. All right. If I were to solve this little mini problem here, 22 times 2.1 times 12 comes out to be 554.2. Oh, sorry, 0.4. Because this is a multi-step problem, what is really happening is all these problems should be combined into one calculation. So I'm actually not going to do sig figs just yet. Okay, I'm going to save it for my final step here. The next portion of this graph is this part right here. Okay, that is melting from a solid to a liquid. Now there's no change in temperature, so I can't use the heat equation. I have to use my other one. This is Q equals the mass times the heat of fusion, because fusion is the process that is happening in this melting stage here, okay? The mass is 22 still. The heat of fusion for water, I need to look that up. All right, I am at water in my table. Heat of fusion for water is 335 joules per gram. 335. So 22 times 335 equals 7,370. The last portion is this one right here. Okay? That last portion in purple is a liquid heating up. We've already melted. We're done with that red portion. Now we've melted into liquid, and we're going to be heating this up. Q equals M times specific heat times delta T. The mass is 22. The specific heat for liquid is 4.184. And the change in temperature, well, we are at 0 when we're done melting, and we increase to 21 degrees Celsius. So 0 to 21, that's a 21 degree temperature change. This comes out to be 22 times 4.184 times 21. Let's see, 1,933.008. All right, my final step would be to add this value to this value to this value. And that is my final answer for the problem.